All right, let me start with a little puzzle that used to bother me, and I mean really bother me, the way a loose tooth bothers you when you can't stop poking it with your tongue. Suppose I ask you a very simple question. What is energy? Not how much of it something has, not how to calculate it, just what is it? Now here's the funny thing. You can go through your entire education, ace every physics exam, work at the frontiers of science, and still, if you're honest, you'll hesitate. You'll feel this little pause. Because the word energy sounds like it ought to mean something tangible, like a substance, like a fluid, like a kind of invisible gasoline sloshing around inside the universe. But it isn't. And yet, despite not really knowing what it is, we can predict it with absurd precision. We can send a spacecraft past Saturn using it. We can design a laser. We can explain why the sun shines and why you're warm sitting in your chair. We can calculate it down to 12 decimal places. That's already strange, isn't it? How can you be so good at keeping track of something you can't quite put your finger on? Let me make it worse. Imagine you have a box. Inside the box are some objects. You don't know what they are, but you're told there are exactly 28 of them. Every day, you open the box, count them, and sure enough, there are always 28. Sometimes they're arranged differently. Sometimes a few are hidden in corners. Sometimes one is stuck under a flap you didn't notice at first. But if you're clever enough, if you look carefully enough, you always find 28. Now suppose one day you open the box and only count 27. You panic. Something is wrong. You search harder. You check the corners. You lift the flaps. You look under the lining. And finally, there it is. The missing one was hiding somewhere unexpected. Energy behaves exactly like that. Except, and here's the twist, you never actually see the objects. You only see the accounting. You never open the box and point to energy and say, there it is. That's energy. What you do instead is notice that whenever something happens, when something moves, heats up, lights up, stretches, vibrates, there's a number you can calculate. And that number has a remarkable habit. No matter what complicated nonsense the universe gets up to, if you add everything up properly, the total stays the same. That's it. That's the whole miracle. And it sounds almost trivial until you realize how outrageous it is. Think about it. A rolling ball smacks into another ball and stops. Where did the motion go? It didn't vanish. The balls get a little warmer, the air wiggles, the floor trembles, the sound fades away. If you're sufficiently obsessive, and physicists are very good at this, you can chase that lost motion through heat, vibration, sound, radiation, and microscopic jiggling of atoms. Add it all up carefully, and the same number is still there, quietly balancing the books. Now you might say, aye! So energy is just motion then. Nope, that's only one costume it wears. All right, maybe energy is heat. Nope. That's another costume. Maybe it's stored in springs, or batteries, or food, or mass itself. Yes, and also no, the trouble is that energy is not a thing. It's a number. A very special number. A number we invent, though the universe stubbornly agrees with it, to keep track of change. That should already make you uneasy, because we're used to the world being made of things. Chairs, atoms, light fields, even space and time, depending on how adventurous you're feeling. But energy doesn't sit alongside those. You can't bottle it. You can't point to it. You can only compute it. And yet, this number governs everything. If you want to know whether a chemical reaction can happen, you ask about energy. If you want to know whether a star will collapse or explode, you ask about energy. If you want to know why time seems to move forward and not backward, well, you're already drifting toward energy again, whether you like it or not. So here's the paradox that always delighted me. Energy is the most important concept in physics, and at the same time, we don't know what it is. That's not a failure. That's the point. Because physics isn't about telling you what the universe is made of in some poetic, satisfying sense. It's about discovering the rules by which the universe keeps itself honest. Energy is one of those rules. A bookkeeping principle so strict that the universe never violates it, not once, not even a little. You can disguise energy. You can spread it thin. You can lock it up where it's very hard to find. You can transform it from one form into another until it barely resembles what you started with. But you can't cheat it, you can't destroy it, and you can't create it out of nothing. And the really astonishing thing is this: the universe didn't have to be this way. There is no logical necessity that says the total should stay the same. It could have been a mess. Things could have popped in and out of existence with no pattern. Motion could have simply disappeared. Heat could have evaporated into nothing. But instead, we live in a universe where beneath all the apparent chaos, there's a calm, unbreakable numerical order humming away. Every time something happens, the universe quietly whispers, "Don't worry." The books still balance. Now, once you notice that, curiosity takes over. You start asking dangerous questions. Why does this number stay constant? What does it have to do with motion, with forces, with time itself? Why does nature seem to care so deeply about this invisible accounting rule? And once you start asking those questions, you're already on the road not toward a neat definition, but toward something much more interesting. Shall we keep going? Good. Because now that we've admitted cheerfully, I hope, that we don't quite know what energy is, we're free to do something much more productive, play with it. Let me tell you how I first really started to make friends with this idea. Not by memorizing formulas, those come later, but by poking at nature the way a curious child pokes at a mechanical toy to see what rattles. Imagine a child with a set of toy blocks. The parent knows there are, say, exactly 28 blocks. The child builds towers, knocks them down, hides some under the rug, stuffs a few into a pocket, stacks others behind the sofa. Chaos everywhere. But the parent, patiently counting, always finds 28. That's energy. The child is the universe, gleefully rearranging things. The parent is the physicist, slightly neurotic, counting obsessively and discovering that something never changes. Now here's where it gets interesting. Suppose the child hides a block in a place you didn't even know existed. A little drawer you forgot about. Suddenly your count is off. You don't say, well, the blocks are gone. You say, aha! There must be a new place blocks can hide. That's exactly how new kinds of energy get discovered. We didn't invent thermal energy because it sounded nice. We invented it because motion kept disappearing. A moving object would slow down, and we'd say, where did it go? Then we'd notice things getting warm. So we added a new hiding place in our accounting system, heat. Later, we noticed chemical reactions giving off warmth and light, and we said, all right, energy can hide in chemical bonds too. Then electricity, then magnetism, then mass itself, which is the sneakiest hiding place of all. Every time energy seems to vanish, it's not a crisis, it's an invitation. Let's do a simple experiment you can try in your head. Take a ball and lift it up. Your arm gets a little tired. You put the ball on a shelf. Now it just sits there. Nothing's happening. No motion. No heat. It looks completely boring. But something has happened. You did work lifting it. And now if the shelf breaks, the ball falls, speeds up, smacks the floor, and makes a sound. Where did all that drama come from? We say the energy was stored in the ball because of its position. Gravitational potential energy, if you like fancy names. But don't let the name fool you. The ball isn't filled with anything. There's no glowing substance inside it labeled energy. What there is a relationship between the ball and the earth, a kind of tension in the rules of motion that says, if you let go, things will start moving. Energy lives in relationships. That's a very important clue. Take a stretched spring, or a bent bow, or a compressed air tank. Nothing's moving, and yet you're nervous standing in front of it. Why? Because you know motion is waiting to happen. Energy, in that sense, is the universe's way of keeping track of its own promises. If the conditions are right, something can happen, and the amount it can happen by is carefully tallied. Now let me ask a question that sounds silly, but isn't. How does the universe know how much energy something has? It doesn't, of course. We do the knowing. Energy is a concept we invented because it works, and it works ridiculously well. You calculate energy using formulas, TMV dies for motion, for example, and at first that looks like just a trick. But then you discover that the same number shows up again and again in completely different situations. That's the shock. That's when you realize you've stumbled onto something deep. You push a box across the floor. It slows down. You calculate the work done by friction. You measure the temperature increase. The numbers line up over and over. It's as if the universe is daring you to stop believing in energy, and every time you try, it calmly proves you wrong. Here's another way to think about it. Nature is very economical, but not in the way people usually mean. It's not that nature is stingy with energy. It's that nature is stingy with rules. Instead of inventing a new explanation for every phenomenon, it uses the same accounting system everywhere. Electrical energy flows through wires. Chemical energy fuels muscles. Nuclear energy holds atoms together. Radiant energy travels as light. Completely different characters, different costumes, different stages. But behind the scenes, the same accountant is at work, tapping the ledger and making sure nothing funny happens. And that accountant never sleeps. Now, you might wonder, why not just describe everything in terms of forces and motion? Why invent this abstract number at all? Because energy lets you ignore the details. That's its secret power. If I tell you exactly how every atom in a system moves, you'll be overwhelmed. But if I tell you the total energy, suddenly you can make bold predictions without knowing every microscopic detail. You can say, this reaction can't happen, or that machine can never be more efficient than this, or this star must eventually burn out. Energy is a shortcut to wisdom. I used to enjoy telling students that physics is like playing chess with the universe. You don't need to know why your opponent chooses a particular move. You only need to know the rules that can't be broken. Energy conservation is one of those rules. It lets you say with absolute confidence, that move is illegal, even if you don't know what move the universe will make instead. And this is where curiosity really kicks in. Because once you see energy as a kind of universal bookkeeping, you start noticing strange things. For example, sometimes energy doesn't look positive at all. Sometimes it's negative. Sometimes you can only define it relative to an arbitrary zero. Sometimes you can shift the entire scale and nothing changes. That's very unsettling if you're used to thinking of energy as a stuff. Imagine if money worked that way. Imagine if I told you, you don't actually have a fixed amount of money. You only have money relative to some chosen reference, and I'm free to change that reference whenever I like. You'd be furious. But nature shrugs and says, works fine for me. And yet, even with that flexibility, even with that abstractness, the differences in energy, the changes are absolutely rigid. Those are what drive everything. So energy turns out to be both slippery and unforgiving. You can't pin it down as a thing, but you also can't escape its consequences. Once you get comfortable with that, once you stop demanding that energy behave like a physical object and let it be what it really is, a deep numerical pattern, you're ready to look at the truly strange part, because now the obvious question isn't, what forms does energy take? Why does this bookkeeping rule exist at all? And to answer that, we have to wander into some ideas that seem, at first glance, completely unrelated: symmetry, time, and the quiet fact that tomorrow behaves an awful lot like today. That's where things start getting deliciously weird. Shall we keep going? All right. Now we're standing at the edge of the really peculiar part, where energy stops feeling like a clever trick and starts feeling like a message from the universe, written in a language we almost understand. Let's begin with something so ordinary you've probably never questioned it. You do an experiment today. You do the same experiment tomorrow. Same setup, same conditions, same care. And you expect the same result. Why? That expectation is so deeply wired into us that it barely feels like an assumption. Of course tomorrow behaves like today. Of course the laws of physics don't wake up in a bad mood and decide to try something new. But stop for a moment and notice how bold that belief really is. There is no logical requirement that the universe must be consistent over time. It just is. And we've grown comfortable with that miracle. Now here's the astonishing connection. The reason energy is conserved, the deep underlying reason, not just the observed habit, is tied to that quiet sameness of time. If the laws of physics are the same today as they were yesterday, then energy is conserved. That's not poetry. That's mathematics. And it's one of the most beautiful results we've ever stumbled upon. The idea comes from a profound piece of work by Emmy Noether, who showed that every continuous symmetry of nature corresponds to a conserved quantity. If space looks the same everywhere, momentum is conserved. If directions are equivalent, angular momentum is conserved. And if time behaves the same from moment to moment, if the universe doesn't care when you run an experiment, then energy is conserved. So energy conservation isn't a mysterious standalone rule. It's a consequence of the universe's indifference to the passage of time. Let that sink in. Energy exists because tomorrow is like today, or, to put it another way, if the universe started changing its rules over time, energy would quietly stop balancing its books. That's already a little dizzying. Energy, which we often imagine as something concrete and powerful, turns out to be a shadow cast by a symmetry. A bookkeeping number born from the simple fact that nature doesn't keep a calendar. Now, this helps explain something that always confused people: why energy takes so many different forms and why those forms can look wildly unrelated. Motion, heat, light, mass, electric fields, why do they all contribute to the same total? Because energy isn't about the stuff, it's about the invariance. Whenever you can shift something in time without changing the underlying rules, there's a quantity that stays the same. That quantity is what we call energy. The specific formula depends on the system, but the conservation doesn't. This also explains why you can redefine what zero energy means without breaking anything. The absolute value isn't sacred, only the changes are. Only the differences that drive motion, reactions, and transformations matter. That's deeply counterintuitive. We're used to thinking that if something exists, it must have a definite amount of it. But energy laughs at that instinct. You can add a constant to all energies everywhere, and the universe doesn't notice. Nothing observable changes. The equations still work. The motions still happen. So energy is real, but not in the way a chair is real. It's real in the way a rule is real. Now let's make this even stranger. At very small scales, energy doesn't behave smoothly at all. It comes in chunks, quanta. You can't have half a photon of light any more than you can have half a child, though both would cause considerable trouble if you tried. Energy jumps. It exchanges itself in discrete packets. And yet, even there, even in the jittery probabilistic world of quantum mechanics, the bookkeeping still works. On average, precisely, relentlessly. Particles appear and disappear. Virtual processes borrow energy briefly, like mischievous children sneaking blocks out of the box, but only for a time so short that the universe allows it. The rules loosen, but they never break. The ledger always comes out balanced in the end. This is where people sometimes start talking about violations of energy conservation. That's mostly a misunderstanding. The universe is subtle, not sloppy. When energy seems to misbehave, it's usually because we haven't accounted for time properly, or we've ignored a field, or we're looking at too small a slice of reality and mistaking a temporary fluctuation for a permanent theft. Energy conservation is astonishingly resilient. It survives relativity. It survives quantum mechanics. It even survives our attempts to get free lunches. Ah yes, the free lunch. Every generation rediscovers the dream of perpetual motion, a machine that runs forever, or produces more energy than it consumes. And every generation rediscovers, painfully, that the universe does not negotiate. You can be clever. You can be subtle. You can hide energy in places people didn't think to look. But you can't beat the accounting system. That's not because physicists are grumpy skeptics. It's because the universe has been tested over and over in every imaginable situation, and it never once lets energy appear from nowhere or vanish into nothing, except perhaps on the grandest scale of all. And now we're really pushing it. When you start thinking about the entire universe, questions that were once tidy become murky. What is the total energy of the universe? Is it conserved? Is it even well defined? Here things get deliciously uncomfortable. In general relativity, energy is not always globally conserved in the way we're used to. Space itself can stretch. The universe can expand. And in an expanding universe, the old notion of a single, universal energy ledger starts to wobble. Photons lose energy as the universe expands. Where does it go? Into space itself. But what does that mean? Space isn't a thing you can hand energy to, at least not in the old way. Some physicists suspect that the total energy of the universe might be exactly zero. Positive energy in matter balanced by negative gravitational energy. A perfect cosmic bookkeeping trick. Something from nothing, but with the books still balanced. Is that true? We're not entirely sure. The universe is a big system, and we're stuck inside it trying to do the accounting while the ledger is on fire. But even here, even at the edge of what we understand, energy remains the guiding idea. The question isn't whether it matters. The question is how far its authority extends. And that brings us naturally to the last and perhaps strangest thought of all. Energy isn't just about motion and change. It's tangled up with time itself, with the direction things happen, with irreversibility, with the fact that memories point one way and not the other. Once you notice that, you start to see energy not as a number we calculate, but as a clue. A clue about why the universe unfolds the way it does and why we experience it the way we do. And that's where I'd like to end, not with an answer, but with a sense of wonder big enough to live with the question. Just one more step, and we'll zoom all the way out.